In this class, we are going to see about the magnetic materials. In the previous class itself, I said some material having attractive property over another magnetic substance, like iron, nickel, copper. These are other magnetic substances. Why the magnet alone showing the magnetic property? I gave the explanation to you. Can you remember anybody? Why is some material giving magnetic induction on magnetic substance?
Presence of unparalleled.
Did I give like that? No. The material is made up of atom. Not only the material, all the materials are made up of atom. Here the magnetic material also made up of atom. Inside the atom, the electrons are revolving. You might know. Not only revolving the nucleus, they themselves spin. We studied already that the movement of electron gives current. Here also the electrons are not at rest, they are revolving around the nucleus. That is the nucleus. This is the electron revolution. It is in the clockwise direction. Another one is in the anti-clockwise direction. Here electron is revolving. Due to the revolution, the atom will have some current. That current is cancelled by the another electron revolving in the opposite direction. Suppose if it is rotating in the clockwise direction, let it be rotating in the anti-clockwise direction. So they can cancel each other. I said so many times, wherever the current is present, there will be a magnetic field. They are all brothers and sisters. Okay? So, the electron revolving in the clockwise direction give some magnetic effect to the atom. In the same way, the electron revolving in the anti-clockwise direction also gives some magnetic property to the same atom. As the revolutions are opposite direction, their magnetic property also cancel each other. The net resultant magnetic moment due to the rotation motions of electron can cancel each other. So you can write resultant magnetic moment due to rotations of electron is 0. However, the electron is not only rotating the nucleus, they themselves spin like the movement of Earth around the Sun. Because of that, also how some magnetic effect will present in the atom. If we consider different states in the atom, each state might have 2 electrons. One electron may revolve in the anti-clockwise, clockwise. Another one may be in the anti-clockwise. These two spin can cancel each other in the first state. In the next state, may be 2. The last state has unpaired electron. Due to this unpaired electron alone, the atom has some electric effect. This electric effect yield the magnetic moment to the atom. So you can say in a single word that due to the unpaired electron, we are getting magnetic moment of an atom. Next. So you are all clear that why the material is showing magnetic property means the material itself made up of atom, the atom itself having magnetic property. So the material made up of this type of atom will give magnetic effect over the magnetic substance. That's all something about the magnetic material. Now we can classify the magnetic material into 3 types. You might know what are the types of magnetic material. Say you studied only up to this. Now you have to study more than that. Ferromet is split into anti-ferro and ferrite. In what way these materials are differ with each other? The first case one is diamagnetic material. In the diamagnetic material, there is no permanent magnetic moment. There is no permanent magnetic moment. What does it mean? Magnetic moment means you are saying about the atomic magnet or tiny magnet. It is named as magnetic moment, represented by letter capital M. Usually the magnetic moment is measured by knowing the length of the magnet and the pole strength of the magnet. Suppose it is a ball magnet, not pole south pole. If you M is the pole strength, if L is the length, by knowing this, you can calculate magnetic moment. So magnetic moment is nothing but the product of pole strength and the length of the magnet. We shall pass to first case, diamagnetic material. In the diamagnetic material, there is no permanent magnetic moment. In the second case, paramagnetic material. Here, there are few unpaired electrons are present. Here, there is no unpaired electrons are present. Because of that, you will have no magnetic moment. Magnetic moments are usually represented by a euro mark. Here the magnetic moments are not aligned parallel to each other. In the case of paramagnetic material. In the case of ferromagnetic material, more or less all the magnetic moments are aligned parallel to each other. This is a spin alignment of magnetic material. What is the next case? After ferro, ferrite, anti-ferro and ferrite. Here, magnetic modes are present, they are equal and opposite. One is up, another is down, one is up. Here, their magnitude values are equal but opposite. Last one, ferrite. Here, magnetic modes are present. They are opposite but not equal to each other. One is up, another one is down with a little bit magnitude. The magnitude values are not equal. This is true in the case of ferrite. So right now, why a magnetic material shows magnetic property? This is given from here. Second case, we split the magnetic materials as dia, para, ferro, anti-ferro. Then how the magnetic moments are present? In a diamagnetic material, no permanent magnetic moment. In the case of paramagnetic material, the magnetic moments are present, but they are randomly aligned. Next case, ferromagnetic material, their magnetic moments are aligned parallel to each other. Antiferro magnetic moments are aligned or arranged equal and opposite manner. The last case, ferrite, here also magnetic moments are aligned or arranged equal, not equal, but opposite to each other. Opposite to each other, their magnitudes are not equal. Okay? So we pass to next one. Children, we shall see domain theory. What is domain? Where it is present? And why a ferromagnetic material does not show magnetic property before it is subjected to external magnetic field. First one, what is it? What is domain? Tamil Nadu is a domain in India. Domain is a small part where the people are speaking only Tamil. In the same way, domain is a small part in the ferromagnetic material. What is the property of ferromagnetic material? How the magnetic moments are aligned? One of you. I draw the diagram. In what way the magnetic moments are aligned? Louder. Parallel to each other. Magnetic moments are aligned parallel to each other in a ferromagnetic material. Even though the magnetic moments are aligned parallel to each other, the ferromagnetic material does not show any magnetic property before it is subjected to external magnetic field. Why? The scientist give the explanation very wisely. He said, let it be a ferromagnetic material. For our understanding purpose, I spent only 4 domains. 1, 2, 3, 4 domains. This is a ferromagnetic material. In this ferromagnetic material, so 4 domains are present. How many domains are present? 4 domains. 4 domains are present. The ferromagnetic material does not show any resultant magnetic moment because the domain 1 and 3 are opposite to each other. 2 and 4 are opposite to each other. According to a single domain, it is magnetized to its maximum value. In the same sense, all the remaining 3 domains also magnetized to its maximum value. But the resultant magnetic moment of the ferromagnetic material is 0. This means that their magnetic moment direction is random. One is up, which one is down? See the board. That domain is down. Second domain is side. Third domain is fourth domain left side. So they can cancel each other. As a result, the material does not show any magnetic. Resultant magnetic moment is 0. The reason given by the wise scientist is that each and every domains are magnetized to its maximum value. Though they are magnetized to its maximum value, their directions are random. As a result, they can cancel each other. The resultant magnetic moment of a ferromagnetic material is 0. Next, we shall study how the magnetic. These are the walls. How the walls of the domains are changed with respect to the external magnetic field. Our aim is to make the material to show the magnetic property. Without teaching you can't learn anything. In the same way, the ferromagnetic material will not show any magnetic property unless it is magnetized. It is magnetized with the magnetizing field. See, let H be the magnetizing field. H be the magnetizing field. Using the magnetizing field, we can magnetize a given specimen. The taken specimen is a ferromagnetic material. You are applying some magnetic field. Its direction is left to right. Among the four domains, which domain's direction is favorable to the external magnetic field direction? 1, 2, 3, 4. Among the four domains, which domain's magnetic moment is parallel to the external magnetic field direction? 2. Second domain's magnetic moment is parallel to the external magnetic field. So that domain 1, 2, 3, 4. Second domain will increase its area by capturing the domain which is opposite to the external magnetic field direction. Which domain is opposite to the external magnetic field direction? 4. So, when magnetic field is applied, say 2 Tesla. 2 Tesla is applied. The dimensions of the domain will change like this is parallel. This is opposite. That domain increases its area by capturing the domain which is opposite to the external magnetic field direction. So the domain wall movement is like that. If still further increasing the magnetizing field, what will happen? Instead of 2, if you apply 4 Tesla. In this case, all the remaining 3 domains try to change in favor to the external magnetic field direction. Like this, all the domain will try to rotate in the directions of external magnetic field direction. By this way, only the walls of domains moving. In this class, we saw so far what is domain. Domain is a small region. In the small region, all the magnetic moments are aligned parallel to each other. Are you clear? How many domains are there? Here, how many domains? 4 domains. Next, we studied about the movement of domain walls. What is domain wall? It is a wall which split the adjacent domains. It is a wall or boundary which split the adjacent domains, or may be called as transition layer. So, we just imagine that this is the only 2 domains. One is here, one is downward direction. Let be the domain wall or branch wall. Domain wall or branch wall. The wall is used for transitions of magnetic moments. Transitions of magnetic moments. See, the magnetic moment direction is upwards. In this boundary, the directions of magnetic moments will be changed like this. Before to enter into the second domain, the transition will be completed. So, the domain wall is used for transition of magnetic moments. It is there in the boundary, they will slowly transfer and change. So that is why it is a transition layer or domain wall or branch wall. In this wall alone, the transition takes place. Transition means changes, directions of magnetic moments changes. The wall again further classified into 2 types. Thin wall and thick wall. The wall is thin, the changes takes place abruptly, suddenly. the wall is thick like this, the changes takes place slowly. So the transition will take place very slowly in the case of thick wall. Whereas in the case of thin wall, abruptly. Very clear? What are two types of walls?
thick wall,
Thick wall and
dark.
thin wall. There are four energies associated with the domain wall movements. How many energies? Four energies. What are they? Exchange, energy, interaction. Second one is crystalline anisotropic energy. Third, magnetization energy. Fourth, domain wall energy. Then what is the use of these energies? The first one is exchange, energy, interaction. See, the ferromagnetic material.
இவர் போன பற்றி அதை பண்ண முடியும்
These are the domains present in the ferromagnetic material. We can arrange these domains like this. Arrange this and that one side with the help of exchange energy interaction. The exchange energy interaction is used to align the adjacent domains in the ferromagnetic material. Adjacent domains. These domains and these domains are connected to each other, so they are aligned close to each other. This and this are same direction. They are formed like this. Here, four directions are there. Here only one, two directions. North, south. Four domains again split into two domains by joining with each other. This is done with the help of only the exchange energy interactions. So you can say that using the exchange energy interactions, we can align the adjacent domains parallel to each other. The next one is crystalline anisotropic energy. You might study meter indices. In this case, the crystal has different orientation. 1 1 10, 1 0 1 10, 1 0 0 10 like this. For easier, I consider this vessel as a magnetic material. I have to magnetize with the help of external magnetic field. That means using electromagnetic field. See, this is the north pole, this is the south pole. This is the specimen to be magnetized using electromagnet. The specimen is magnetized in this direction. Along the lengthwise, let it be along the lengthwise. The produced magnetic field has been 3 Tesla. So 3 Tesla is the magnetizing field needed to magnetize a given specimen to maximum its value along the lengthwise direction. Next case, we just change the direction, orientations of the specimen to be magnetized. Keep the material like this. While keeping the specimen in this direction, the magnetizing field Clear? While keeping along the lengthwise, the magnetizing field needed is only 3 Tesla. While keeping this direction, the amount of magnetic field needed to magnetize the specimen to its maximum value is 5 Tesla. Which direction is preferable? Which direction is easy one? The first case, let it be the first case. Let it be the second case. Which case is easier to you? First case or second case? I can say the first case we are using only 3 Tesla to magnetize the specimen to its maximum value. That is, it is magnetized to its maximum value, that is saturated. After that it is not magnetized. Second case, we are keeping that specimen like this. The orientation is changed. In this case, we are giving magnetizing field 5 Tesla. We are giving more magnetizing field in order to magnetize the specimen to its maximum value. So this is the hot direction. This is the easy direction. Which one you will prefer? Easy direction or hot direction? Easy direction. How much energy difference between these two? That is called crystal anisotropic energy. The difference in between the hot and easy direction is called crystal anisotropic energy. The difference in energy between the hot and easy direction is called crystal anisotropic energy. Next one is magnetization energy. You might study that when a ferromagnetic material is subjected to an alternate magnetic field, when a ferromagnetic material is subjected to the alternate magnetic field, during magnetization, all the magnetic moments are aligned in a particular direction. All the magnetic moments are aligned in a particular direction during the magnetization. During the demagnetization, all the magnetic moments are randomly aligned. We just imagine if you align all the chalk in parallel to each other means the length will be more. If the chalks are aligned randomly means the length will be reduced. Now, this is the first domain. This is the second domain. Align the parallel. The next one also aligned parallel. It is present when the magnetizing field is acting on it. When the magnetizing field is removed, they are randomly aligned. One is like this. In this case, the length of the specimen is shrink. Length of the specimen will be shrink. So the expansion and the shrinking will take place while the magnetizing field is applied on a ferromagnetic material. If this takes place at a fast rate, the ferromagnetic material length will change at a fast rate. This gives some valuable energy called ultrasonic sound. That is called magnetization effect. When a ferromagnetic material is subjected to an alternate magnetic field, the ferromagnetic material expands and shrink at a fast rate. That means it vibrates at a fast rate. All the vibration will produce sound now. This vibration will produce ultrasonic sound. The energy associated with the magnetization effect is called magnetization energy. What is magnetization effect? The change in length of a ferromagnetic material when it is subjected to the external magnetic field. The energy associated with the magnetization effect is called magnetization energy.